Hello, kicking off the 2019 map, so multiple choice time with question A. That equation has how many real solutions? Well, they've given us coefficients annoying enough to make it difficult to factorise. So, well, let's look at, we know it's going to be doing something like that at its most extreme. See if we've got any turning points. 3x squared would be equal to 300. So we're going to have turning points at x is plus or minus 10. So that's at minus 10, that's at plus 10. So where is this 3000 fitting amongst all of this? So that value there is going to be minus 1000 plus 3000. So that's still less than 3000. We're only going to get one solution somewhere up here. So exactly one solution B. Question B, product of a square number and a cube number is what? Always a square, never a cube, always a cube, never a square, sometimes, never, never, always, always. Product of a square number and a cube number. Well, if you do 1 times 1, so, well, it can't be that because that is a cube number, so it's not going to be A. Never a square number, not going to be B. Never, never, so it's got to be C or E. Right, let's try another one then. So we want always something to be, we just need one where it doesn't work then. So a cube and a square. So if we do 1 times 4, then that's a cube, that's a square, and that answer isn't a cube, so it's got to be C. That's a bit of a weird question. C, the graph of that is sketched in which one? Right, usual starting point, x is 0, then we're getting y is 0. So it's not A then. So let's got rid of that one. X is 0, y is 0. These are all even powers, so y's got to be positive all the time. So it's not going to be E. Then what else have we got? Then are we going to get anything? Well, if this isn't just going on forever, when sine x is 1, we're going to get infinity appearing, aren't we? Because we're just doing 1 added up forever. So at 90 degrees, we're going to get this. So it must be D. That's the only one that's got asymptotes on it. So it's going to have to be D. Question D. Area between the parabolas with those equations equals 9. Possible values of A are... Okay, so we want to get the difference in the integrals, but we need to know what range to integrate over. So we're going to need to find out where they intersect with each other. So we'll have x squared plus 2ax plus a is equal to a minus x squared. Cancel those. We can cancel some 2's as well, can't we? Because we'll have 2x squared and then get rid of that and get rid of that. So we've got that x is 0 or that x is minus a. So we've got those. So we want to then do the, well, we can just do the modulus of the difference of the integrals. So we go from minus a to a of this x squared plus 2ax plus a dx, and the minus a minus x squared dx. This is going to be a lot more long-winded than the previous ones, and that's got to be equal to 9. So, oh good grief, this is just rubbish, isn't it? So we got x, well, we can ignore all of the, well, it doesn't really matter which way around we put the a's either, because we're flipping all these around, taking the modulus on it all. But anyway, let's do x cubed over 3 plus ax squared plus ax, 0 minus a, and then here we've got ax minus x cubed over 3, 0 minus a, and that's got to be equal to 9 when we do the mod of it all. Oh, good lord. Right, so we're going to have then a minus a cubed over 3 minus a cubed, and then minus a, no, that would be a, oh, right, I'm going to have to go back and check my minuses here. So that would be a minus a cubed over 3, but then we're minusing it off, so that would be a plus. and then that would be a plus, and that would also be a plus. So they're all pluses. Right, the way I've got it written anyway. So we've got all of those, and then we've got our oh no, the middle one's going to be a minus, isn't it? Because we're squaring it. Oh, good grief. Right, let's do this again. I'll get myself into a right mess here. So that would be minus a cubed over 3. Then we're subtracting it. So a cubed over 3. Then we got plus a cubed. So that would be minus a cubed. Then we've got minus a squared, which would be plus a squared. Right, okay, that's better. Then we've got our minus a squared, which becomes a plus, which becomes a minus. And then we've got the minus a cubed over 3, then becomes plus, which then becomes minus, it then becomes plus. And all of that has got to be equal to 9. So we're getting rid of those. So, and then we've got 2/3 minus 1/3, so a cubed over 3 is equal to 9. So we've got the a cubed, the modulus of a cubed is equal to 27. So a is plus or minus 3. Okay, I made a bit heavy work of that in that bit in the middle, just getting all my minus signs messed up. I think I would have been better with just flipping these limits around, but it comes out fine in the end. Right, but yeah, made heavy work of it. E, the graph of that is what? Is it empty? Is it not empty but has no straight lines? Includes one line, two lines, many lines. Well, is this symmetrical? We've got the same things here. We've got sine y, sine x, cos x. Let's rearrange this. It looks like we've got sine y plus cos squared y is sine x plus cos squared x. Excellent. So we've got it solves for x equals y is a tick. So we certainly need that then. So we're going to have the y equals x line. So it's not empty and it does have a straight line. So how many straight lines will it have? But these things are all cyclical. So, or cyclical, might be another way of putting it. So if you have y equals x plus 2 pi, yeah, we could have that. You can just move that along 2 pi. You can change it as much as you want. You just keep on cycling it. So it's going to be E. F, in the interval 0 to 360, that equation has how many solutions? Right. Yeah, let's do some sketching then. So we've got, let's start sine cubed. So we start with sine. We're only doing one flip along. So we cube it up. So we're going to have those points are going to stay where they are. They're going to stay where they are, but we're going to be doing this sort of thing. So that's our sine cubed. X, cos squared. So that's our cos. Then we square it. So we're going to be getting that down to there, up to there, down to there. Just trying to get it to match up a little bit better. So we've got those, and we need to add up these two to get them to equal 0. So that can only happen in that portion, which is from there to there. And when we're here, we've got 1 is our total at that point. When we're here, we've got -1. And when we're here, we got 1 again. So we must equal 0 once on the way down and once on the way back. So that's going to be 2 solutions, which is C. G, let those equations, A, B, C, all greater than 0, do they specify them all uniquely or don't, or whatever? What combinations? Can we solve them, essentially, is what we're saying. So we've got A to the power of C is B. We got b to the power of c plus 3 over 2 is a. Okay. And then we've got c to the power of b is equal to a. Oof. Right, well, it feels like we can combine these top two. That looks quite good, doesn't it? Because if we do that to the power of c, so a to the power of c is equal to b, which is equal to a to the power of c is equal to b, and it's also equal to b to the c plus 3 over 2 to the power of c. And that is equal to b to the power of c squared times b to the 3c over 2. Right. So what am I doing with that then? Oh, we can compare these coefficients actually, can't we? We could say, if I just left that as one lot of b, we can say, well, 1 has got to be equal to c, not coefficients, powers, c squared plus 3c over 2. Right, so we've solved for c then, but assuming we can get a solution for it. So 2c squared plus 3c minus 2 is equal to 0. Is that going to factorise? It is going to factorise. We're going to have 2c, we'll have a 1 on that side. We have to have the 2's on opposite sides. That have to be a plus and a minus. So we've got c is minus 2. It can't be minus 2 because they're all greater than 0. So that means that c is equal to a half. So we fixed c. And so it's not d. Right, so we fixed c anyway. So what are we now doing with all of this? If we fixed c, we've got that a is, well, the square root of a is b. So a is b squared. We've got that. Oh, we've also got this thing. A is b. Have I just done this twice? C is a half. Yeah, a is b squared. I've just done that twice. And also that is equal to a half to the power of b. Ooh. Right, how are we going to deal with that? B squared is half to the power of b. That's not pleasant, is it? Right, let's look on a graph then. So if we had a is b squared, we only have to care about positive a. So that's doing that. A is b squared. Okay. And then we got half to the power of b. So this is our a, this is our b. We've got a is b squared, and half to 0, so it's going to go through half to the power of b. Yeah, wow, we're going to get this horrible looking. So it's going to go through here, it's going to go through 1. And as b increases, this is getting smaller and smaller and smaller. So we're just going to have one solution for whatever a and b are for that c. So we've got a unique set of values, which is a. That was difficult. The triangle ABC is right angled at B. Right, let's get a look at that then. So right angle B, A, C. Follows the side lengths are positive numbers in geometric progression. Well, that's got to be the longest one. So say that was x. That's our short side. Then we'd have ax and a squared x. So that's what we got for those sides. Follows that tan BAC is either that or that, BAC. So here we got that. So in this case, trouble is we could have drawn it the other side, couldn't I? Could have done that one. So we've got tan BAC is equal to either A or 1 over A. That's what we're getting for that, isn't it? Okay. So, and we also know that we can, well, if we square these things up and add them, so we're going to have x squared plus a squared x squared equals a to the 4 x squared. So get rid of all those x squareds. So we've got a to the 4 is equal to a squared plus 1. So let's do let b equal a squared. So we've got b squared minus b minus 1 is equal to 0. So we've got that, which means that b is going to be equal to, can't even remember what I'm working out here, b is a squared. God, it's going to be, this is why we've got so many square roots in these answers. Yeah, so on this we've got 1 plus or minus the square root of b squared, so 1 plus 4, so that's our root 5, so that's come in nicely. So that's ruled out b and e already by the look of it, over 2. So that's one option for B. That's a squared, which could be either one of these. So we need to square root this thing. Good Lord. Right, so we've got the square root of B. Well, this, we can't have the minus then, can we? Because we're square rooting it, and root 5 is greater than 1. So it's going to be a square root of 1 plus root 5 over 2. Does that turn up anywhere? Well, square root, yeah, so we've got it here. And we've got it here. And we've got it here. Right, so that hasn't helped in the slightest for ruling out those. But it's got to be this 1 over a then. So we need to do 1 over this thing. So if we do 1 over it, we're getting 2 over 1 plus root 5. So we're going to want to do 1 minus root 5 multiplied top and bottom. 1 minus root 5. So we're going to have 2 minus 2 root 5. I don't know why I've expanded that bit at the top, because what we're getting at the bottom, we're getting 1 minus 5. So we're getting minus 4 on the bottom. So we're getting root 5 minus 1 over 2, and then square root all of that. So that is, no, it's not A. That's the wrong way round. So it's not that one. Here we go. It's this one here. So it looks like C, and that one's got the minus on the outside. So C, that was a fiddly question. Quite a nice question, but it was a fiddly question. Right, I, we got 2 to go. Positive real numbers X and Y satisfy X is between 0 and Y, and that. So what solutions are we getting? Good grief. Right, this might be another graph. Let's try and visualize it. It's been graph heavy, this, isn't it? Graph heavy indeed. So we've got positive X. So when X is 0, we're just getting 0. And then as X increases, it's just getting bigger and bigger and bigger. So we're doing that. Okay. Now Y is bigger than X. So it's going to get, it's just going to be bigger all the time. But neither of them can actually be 0. So we don't get that intersection, and they're not going to intersect anywhere else. So we're not going to get any solutions. So it's going to be A. Right, that was easier than it looked, that one. But again, another graph sketch in this. This has been graph heavy. J, the last one, an equilateral triangle with center O, side length 1. Right, let's draw that out. Equilateral triangle, side length 1, center O. Straight line through O intersects a triangle at 2 distinct points P and Q. Minimal possible length. Minimum length of PQ. Well, it's not going to be going through here, is it? That's going to be much longer than... So we're going to want to be parallel to one of the sides, I would imagine. Yeah, because we're going to want to make this another... equilateral triangle. I lost my words there. So that is definitely going to be shorter, and as you move it round, it's going to be getting longer. So that's what we want. We want to go parallel to one of the sides. So what's our new setup that we've got then on that? We've shrunk down. We're going through the middle. This is, yeah, let's try and get a better looking picture than this now. I've scrolled over it. Yeah, the thing is, that doesn't look anything like an equilateral triangle. But we have to have a line that goes through this that's parallel to that. So we have to shrunk it down. We've got similar triangles here. And we've shrunk the height down. You know, we always know if you've got these triangles, you've got 2/3 to 1/3. You know, on the equilateral ones, you can easily set that up. That if you draw out the triangle, put the middle in there, and split this, and think, well, that's got to be 30 degrees, that's got to be 60 degrees. So you can easily then see doing a sign of it that if you've got 30 degrees here, then whatever this height is going to be, that's going to be half of it. And you add those up to get the height of the whole thing. So we're splitting that into a ratio of 2 to 1. So we know that the center is 1/3 of the way up the height of the triangle. So in this case, we've reduced the height down to 2/3, which means we've reduced all of the lengths down by 2/3. So it's going to have to be 2/3 is the answer. for that. Yeah, I mean, you can do that little bit of trig if you need to, just to show that you've reduced it down to a similar triangle with 2/3 the lengths. But you can quote, well, you don't even have to quote anything in this because it's a multiple choice question. But it's quite easy to see. I don't think you need to do any kind of working out, really. You just need to visualize, where we're drawing the line. And clearly, we don't want it going through any of the any apex point on this triangle. As soon as it's going through an apex, we've got the highest bit. So we just want to get halfway between going through these apexes, or at least that short length as we're cutting off another equilateral triangle. So the last two questions then weren't too bad. The I and J were okay. H was certainly manageable. It was just fiddly. That was long-winded. G, I would say G, as a log question goes, was pretty tough. F was just sketching out graphs. That wasn't too bad. E was weirdly straightforward. I suppose it was quite intimidating in what they were asking for. D was long-winded, very long-winded, and I nearly made a mess up on the limits, but providing you don't rush it. I think I was just rushing it a bit on D. C was, that was fine for a graph identifier. B was weirdly easy, and A was fine again. Okay, a little bit of insight in A. It was quite a nice question, trying to solve an equation in a different way rather than just looking for roots directly. So nice mix of questions. Not ridiculously easy or crazily hard. They were sort of well pitched, I think. It was kicked this paper off.